Good morning, everyone. Today I'm going to talk about some ideas on the radiative signatures of growing massive black holes in the universe. As already Hannah and Derek gave a nice talk, so I skip the detailed introduction. We discovered the faint AGN in the JWST public data. So here I'm showing the beautiful spectral data here. You can see the broad component of H alpha emission, which allows us to estimate the black hole mass as a 10⁷ solar masses for this particular source. And after this first discovery of AGN within the JWST, so lots of people try to join this game and discover a large fraction of population in the similar redshift 5. And compared to these red sources, mark is red, but color is not, but anyway. So this population is quite new, and opened a new window compared to the other previously known AGN population, the same redshift. And also, beyond the zeroth order, the discovery of AGN, so we have ACD data, and you try the ACD fitting or image decomposition of these sources, you can get the stellar mass for this object. If you plot the stellar mass x-axis, y-axis black hole mass, you can easily find that those JWST AGN population tend to have kind of overmassive properties compared to the local relation in the diagonal line. And people argue that whether or not this apparent distribution is intrinsic or selection bias. But as theorists like me, so anyway, overmassive black holes do exist. We want to explain the pathway to be overmassive domain at the early epoch. So this is the motivation of my talk. And here, so this cartoon picture shows the kind of a diagram for explaining the various theory of seed black hole formation in the early epoch. Skip the detail, but we basically have two different distinguished seeding model. One is the stellar mass remnant black holes, another is a massive seed formation. So in order to explain the overmassive nature of the massive black hole, the early epoch, I try to focus on the massive seed black holes that grow to be a JWST observable range by superidential accretion. So simply, superidential accretion brings the black hole into the overmassive domain, dominating galaxy population. So in theoretical words, so people often discuss the possibility and the physical nature of superidential accretion, also discuss the onset condition, right? How to activate superidential accretion, early epoch, showing lots of papers. And this is, I'm showing just one example of the superidential accreting simulation onto the black hole. So this is a density profile. You have a black hole center, gas is accreting, but black hole try to push the gas because of radiation pressure and heating. But as time goes, the mass is accumulating near the equatorial region, and you have very dense accretion disk eventually collapse to the black hole. So this is a very powerful feeding process activating superidential. So here I show you the kind of light curve, accretion rate history, right-hand side. As you can see, in a very initial stage, accretion rate is kind of episodic around the Eddington accretion. But after some points, so black hole accretion jumped to super high value, more than 100, even a few hundred superidential. So the take-home message here is, if you do high resolution radiation hydro simulations on the black hole accretion system, you can find superidential growth of the seed black holes, say 10⁵ or 6 solar masses. So this kind of event occurs episodically with an individual duration of a few million years. So basically, black hole repeat this kind of interesting burst over the time. If you take this model and try to put the evolution track on this diagram, you can find this kind of characteristic evolution pathway on this diagram. So if you believe this kind of radiation hydro simulations on the black holes, you can kind of naturally explain overmassive domain thanks to superidential nature. And another important thing is, the black hole accreting so fast, which means you can expect very bright emission from those sources. So by that, you might also expect, detectability of these sources by JWST might be higher. So let's talk about how to find such an interesting system. So we also use the radiation hydro simulation data and also perform the emission line transfer calculation as a post-process calculations. So combining our RHC simulation and a cloudy calculation, and then we construct the SED here. So we put this AGN at redshift 8 and try to see what's the characteristic nature of the SED here. So thanks to the very powerful and dense accretion disk, right, at the super-Eddington rate on the black hole, this system easily produces very, very strong Balmer emission lines. So namely, H-alpha emission has very large equivalent resistance, over 1,000 angstrom. And this is a natural consequence of the very dense accretion disk surrounding black hole. And also, this accretion disk is so dense, so the Lyman beta photon is tend to be easily trapped in the accretion disk. Then this energy can be reprocessed into the recombination line of the neutral hydrogen. So you have kind of difficulty, but you have a 3O1 emission line. So that could be a kind of nice smoking gun signature that produced by super-Eddington accretion. So the important thing here is if you think about such kind of super-Eddington accreting seed black holes, you have two important things. So one is EW of H-alpha emission is quite high. And also, to produce such O1 emission, you have dense gas around the black hole. So number is 10 to the 9. So please remember this number. Okay, then having this kind of SED, we construct the color diagram to be friendly to observers. So this left panel shows the color diagram using x-axis near-count filter only, and y-axis using MIDI 770 filter. So if you think about high redshift seed black holes, say 10 to the redshift 8 to 14, so within this range, H-alpha emission enters the MIDI 770 filter, so which makes a color 444 minus 770 getting redder. So using this unique signature from super-Eddington accreting seed black holes, we can make some good separation, right? Try to find the seed black holes and separating them from other kind of contaminants, say similar redshift galaxies or nearby galactic brown dwarfs. And also, these super-Eddington accretors has, as I mentioned, so they have very interesting future. So now we have lots of JWST agent observations. So that tells us, again, two interesting things. One is, so if you look at the JWST identify AGN, the distribution of EW of H-alpha emission tend to be higher compared to sloan quasars, say by factor 3 higher. And also, more than roughly, say, 20% of broad-range AGN are reported by lots of observations. So those AGN tend to show Balmer absorption, which indicate the presence of dense cloud around the massive black hole, again, density is 10 to the 9. So I believe those two features are kind of consistent, right? Not the contradiction to the predicted characteristic signature of super-Eddington accretion onto the seed black holes. And using last 5 minutes, I'm gonna slightly switch to another object. This is a little red dot. So the little red dots, right? We already discussed a lot of things. So they are very interesting. Source, very compact. The red color also showing broad component of H-alpha. So which again indicates presence of AGN. And another interesting thing is the characteristic V-shaped SED. So people argue the origin of SED. We basically have two, maybe blue part, kind of flat or blue, and the rest optical red color. And people argue the origin, but this is very controversial. We're still debating, but we also kind of propose the, this V shape can be the origin of, kind of consequence of the modified extinction law. For example, so if you look at the kind of nearby dense cloud extinction law or agent environment, we actually know the extinction law is kind of deviating from the commonly used Carzetti law, SMC extinction law. If you apply, you basically produce this kind of extinction. But this talk, I want to focus on the another part, the rest of frame near-infrared part, because the longer wavelength SED signature is quite important to make sure or to kill some model, right? Galaxy versus AGN, because if you have, so if the origin of little red dots are obscured galaxy, you might expect some like this kind of tendency, right? If you go to longer wavelengths, flux start to decrease, right? Because you have no such a cold temperature source. But if, on the other hand, so AGN is origin, you might expect a very rapid rising toward the longer wavelengths. So that might be interesting observation study to make sure the origin of little red dots. The result looks like this. So if you have longer wavelengths data, Williams on the Horace Aikens data up to the 20-ish micron, so both results suggest the SED getting flatter. So which actually disfavor the AGN model, right? People claim that. But we try to revival, right? Revival the AGN scenario. It's kind of pessimistic. But we actually try to propose how to survive, or how to make the AGN scenarios recover again. So actually, this cartoon picture is showing temperature distribution around the black holes. So the inner region hotter, warmer, and cold. But the one missing information is the density distribution here. So I try to characterize density distribution using very simple single power profile. Then if you consider so gamma index is higher than 1, which means centrally concentrated dusty medium. So if this is the case, the emissivity peak is actually concentrated near the black hole, right? Most mass, large fraction of mass actually concentrated toward the center. But if you relax this assumption, say gamma is between 0 and 1, so the emissivity peak actually move larger, right? Move to larger radii. So the warmer or cold dust actually produce most of the emissivity from the system. So show the result. So if I assume very steep density profile, so as you can see, you have a very steep rising in the rest of frame near infrared. So that is actually consistent with the classical dust torus model. But relaxing this assumption, gamma 1, gamma 0, you can escape the constraint from the immediate photometry. Also still consistent with the ALMA upper bound at the longer wavelengths. Right, so by that, we suggest, so dust distribution or little red dots might be extended compared to the classical AGN model. And this is kind of parameter survey. But good thing about this model is all the ACD shapes can be controlled by only 2 free parameters. So density normalization and the spectral index gamma. So compared to the very sophisticated clumpy dust model, so I think we are very, very simple, but nicely reproduce the characteristic nature of little red dots. So this is my last slide. Okay, getting better. Okay, then, so in the classical model, the AGN model, people actually have 2 classes, type 1, type 2. So I believe, so this is the consequence of the, very, very mature dusty environment around AGN. So if this is the case, the SED of AGN depends on the viewing angle, right? No matter how much extinction, because this gray brown region is so thick, the extinction magnitude AV is like over 10, right? You have no chance. But if you consider the extended unsettled down system, maybe because the system is younger or outflow is dominating, I don't know. But if this is the case, we can make some intermediate regime of the dust obscured AGN. That might be a little red dot. That's also the reason why we often see little red dots as only high redshift. It's a discussion item. Okay, this is my summary. Thank you for the question.
Questions? Maybe do what?
So can I ask? So you said there's Burma absorption in 20% of AGN and is it so consistent with maybe you did numerical simulation and numerical simulation some instability of the disk can create this kind of high density clump or
yes. Yeah, after I have a discussion with Roberto, I check back to the simulation paper and the data. So we have 10 to the 9 or 10 to the even 10 per cubic centimeter dense gas around the less than point something parsec region, which is actually the region where H alpha emission comes out. So we have both emission and dense cloud. So this calculation actually haven't never considered absorption because 2 years ago, but now we try to reproduce absorption future.
Just a reminder to say your name. So that was Sunyeon Chung, and then we have Roberto, then Priya.
Yeah, thanks. Really great. On the lack of hot dust issue, I think this has been a bit overstated in the sense that all of the vast majority of little red dots that are missing hot dust are actually photometric candidates. And I think, as far as I know, there are only 2 little red dots which are spectroscopically confirmed to be AGNs with the broad lines and which have constraints on the medium frame emission. And one of them has indeed a lack of hot dust, the other has a prominent excess. So what I'm saying is that before, claiming big issues, probably we should wait a little bit for more confirmations on spectroscopic, and based on these only 2 cases, maybe it seems that it's a mixture of your 2 scenarios. Yes.
Yeah, thank you for the comments. Yeah, actually, we don't exclude the possibility of the dense dusty torus, but some system might be more kind of mature, but some system might be younger. So the physical interpretation is kind of easy in this model. It's pretty flexible, I would say, just changing the Paro index, so which also has a physical meaning. Thank you.
Kohei. Yeah, very interesting idea. I'm curious, in the simulations that you did, you do not include star formation, right? This is just black hole growth.
Yes.
So obviously, there's going to be dust that's going to be generated, gas that is going to be taken up by star formation. So the densities may be off. So I was just curious, why not even at least in the post-processing, just add in the stellar component, even if you cannot self-consistently do the interplay between the black hole feedback and the stellar feedback. I understand it's extremely difficult, yeah. Just curious, yeah.
Yeah, thank you. So at the time when we wrote this paper, I was not familiar with observation, so that's why I just removed galaxy population. But now, yes. So I think the galaxy population might be important, the shorter wavelengths here, particularly. But I guess this characteristic feature, H alpha very brightness, would be still important, even though we consider galaxy stuff. But, yes, yeah.
Tracks on your color plot
yes,
that are crucial
especially
for identification.
Especially near yeah, thank you.
Great, one last question from Joe while our 2 lightning speakers come up.
Hi, can you show the plot where you show the accretion rate as a function of time?
Yes.
Yeah, so the question I had was that it's kind of related to Priya's, but I thought the idea was that it's hard to sustain these really high accretion rates because you can't prevent the gas from fragmenting to form stars, and then once it does fragment to form stars, then you've kind of quenched and you have to rely on stellar winds. So, but in your case, you're not forming stars, so basically, just wanted to know if you could comment on that issue.
Yeah, this is a very important issue, but this particular simulation focused on the galactic nuclei. So above, larger than event horizon, but inside the boundary radius, kind of 0.1 parsec innermost cell, up to tens or 100 parsec. This is much smaller than galaxy, but of course we have to include the galaxy, so star formation, stellar activity, but this is missing.
Okay, thanks.
But as long as you supply the gas onto the black hole boundary radius, which is about 10 parsec, 1 parsec, so this simulation is actually fine. But this is the question, another question.
Yeah, okay, thanks.
Okay, let's thank Kohei again.
Thank you.